Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, up next we have our Spotlight presenters, and please make sure you come visit them with all your questions tonight.
Hi, my name is Max Jarleberg, and this is our work on spatial transformer networks together with Karen, Andrew, and Coy at Google DeepMind. And so basically the motivation for this work was that we're missing a key ingredient for neural networks, and that's being able to allow them to spatially warp their data. Normally with convnets, we rely on multiple layers of max pooling to achieve spatial invariance or some sort of inherent pose normalization. But here we define a new module, the spatial transformer, which actually has a differentiable spatial warping mechanism in it. And because it's differentiable, you can just drop it into networks anywhere you want and train it from the global task loss without any extra supervision. And so the result of these spatial transformer networks, which can actually actively spatially warp their data, so conditional on the input, can learn to attend to and pose normalize objects of interest. And here, for example, is the result of a spatial transformer trained to classify distorted MNIST digits. And on the left, you can see the raw input. In the middle is the transformation visualized on that raw input. And on the right is the output of the spatial transformer, which is then fed to the remaining layers of the classifier. So there's three main components of the spatial transformer. First, you have this localization network, which looks at your input feature map and then regresses the parameters of the transformation to apply to this input. So for example, for an affine transformation, this would be the 6 elements of the affine transformation matrix. Then you have a grid generator, which takes these parameters and produces a sampling grid. The sampling grid defines where, for each output pixel, the location in the input that you take the value from. And there's a differentiable sampler which takes this sampling grid and actually does the transformation for you. And so this module, you can encapsulate it and drop it into networks anywhere you want. And the result of these networks which automatically attend to and pose normalized objects of interest. So for example, on the left is, at the top, there's the mean image of a distorted MNIST data set. And if you train a transformer network just on classification labels, the mean image of the output of the transformer is this pose normalized mean image below, which is a lot easier to classify. We show state-of-the-art results on street view house numbers by using multiple transformers deep into the network intertwined with convolutional layers. And we show state-of-the-art results on fine-grained bird classification by having up to 4 transformers in parallel, which automatically learn to focus on different body parts of the birds. There's third-party open source code floating around for this. And if you want to know more, come to my poster and come to my talk tomorrow at the Deep Learning Symposium, where I'll give some more details and show some cool videos and stuff like that. Thanks.
I'm Will Whitney, and I'm going to talk about the Deep Convolutional Inverse Graphics Network. And this is work with Tejas Kulkarni, Pushmeet Kohli, and Josh Tenenbaum. So our goal in this work was to learn a disentangled and semantically interpretable representation for 3D images. And in doing so, we were inspired by the representations that 3D rendering engines use. With a rendering engine, you can specify a 3D model, then tell it where to put that model in the image and at what angle and with what lighting and so forth. And the great thing about that is that the representation of these extrinsic images, like pose and lighting, is totally decoupled from which model you're using. We've managed to learn a model with some of the same properties. With our model, we're able to directly make changes in the latent representation and then re-render images under different conditions. So what we're doing is we're showing the network one image of a face and then basically asking, what would this face look like under different lighting conditions? Or what if it were tipped down some? And the network can generate these images for us. So the model we're using to achieve this is based on the variational autoencoder. First, we have an encoder, which takes in a grayscale image. It has several layers of convolution and pooling, and then produces a distribution over latent representations. Unlike in an ordinary network with distributed representations, we're going to interpret certain components of this representation as having specific semantic meaning. Then we have a decoder, which takes in the latent representation and renders a new image. It has 3 layers of nearest neighbor unpooling and convolution, so it's basically the encoder network flipped around backwards. And we use a special training procedure to learn a representation with this semantic structure that we're looking for. What we do is, during training, we have short video clips with only one of these variables changing at a time. So it's a face rotating up and down, or with the light sweeping from left to right, but not all of them. Then intuitively, what we want is throughout each of these training videos, all but one of the components of our representation should stay the same. One component varies, representing the action in the video, but all the others should be constant. And by enforcing this constraint on the forward pass, and then adding gradients that encourage the encoder to produce these representations on the backward pass, then we can actually get this behavior that we're looking for, where one component of our representation closely corresponds with the one variable that changes during the video. I think that's about all the detail we have time for right now. So if you'd like to hear more, we'll be poster number 6 at tonight's session. And by the way, I'm also applying to PhD programs right now, so if you're looking for grad students, definitely stop by the poster. Thank you.
So my name is Tong Zhang, and this is joint work with my long-term collaborator, Ria. So we are actually looking at text categorization problem, trying to understand whether neural net can do better than what has been done for a very, very long time, the linear classifiers like SVM. So we did something on the supervised, and then we are moving to the semi-supervised. So this is mostly about the semi-supervised learning. But first, I will talk a little bit about what we did for the supervised text categorization. So we probably all know, if you have been around in the community, and I'm included, I'm very interested in text categorization, has done some earlier work in the maybe more than 15 years ago about linear methods for text categorization. At that time, it achieved the state of art, and it has been that way for a very, very long time, until very recently. So recently, there are attempts to do the neural nets on the text categorization problem. So there are a few works, but including ours. So the difference of ours, we try to use the original text as input directly to the convolution neural net. It's a simple convolution neural net structure, but when we find out the softwares, we couldn't find anything which can do that. So we did that ourselves, the implementation. So the idea we really try to play with, and actually it can beat linear methods, but what it really matters, we found that it's a better use of n-gram, basically using region embedding. So for the traditional linear method, you use n-grams plus like linear method and SVM, but here you embed n-gram or a region into a embedding vector, and then you can think about it as a bag of those. So that essentially is the, as far as I know, the state of art for the supervised text categorization. Now, if we move to the semi-supervised, because when we compare methods like supervised method to the tasks like sentiment classification, we know that a lot of people doing, for example, LSTM plus some supervised learning that can do better. So what we look at is that we try to apply our methods on semi-supervised methods to view learning, which is quite a while ago, which happened with the linear methods. But then for the nonlinear method, we extended to CNN using the two-view learning. Basically, we first use two-view to learn an embedding feature, and then added the feature to a CNN. And then we find that this achieved the state of art, as far as I know. So this is the best possible until now. And we also tried some other methods like LCMTM and so on, but this is best. Okay, thank you.
Hi, I'm Rupesh, and this is joint work with my collaborators Klaus Greff and Jürgen Schmidhuber at the Swiss AI Lab. It's here. So deep networks are very powerful models, but they can be very difficult to train sometimes, especially when the number of layers becomes tens or in the hundreds. A neural network is essentially a successive nonlinear transformations of data, and when the number of such transformations is very large, the gradient of the composition of these transformations can vanish or explode, and this causes problems in training. So in this work, we attack this problem using a new architecture called highway networks. In a highway network, every unit learns to smoothly vary its behavior between transforming information or carrying information. This idea is inspired by the gating mechanism in an LSTM network. Due to this design, we can easily bias the network initially towards carrying information. And this way, the gradients don't vanish, and we can train networks with tens to hundreds of layers with gradient descent techniques. In the figure on the right, we show that plain networks cannot be trained well as the number of layers increases to about 100 with a well-known initialization, but highway networks do not suffer from this problem, and we can still easily train them. As training proceeds, every unit in a highway network learns to adaptively transform the data as needed. So some units might transform the data more, other units might want to carry information further. So this has some additional advantages. One of these is that units can easily learn to combine information from multiple levels of abstraction. Another advantage is that we can easily measure the contribution of every unit or any layer in a trained network. So in this figure, we measure the contribution of each layer in two networks. They are each 50-unit networks, and they're both 50 layers deep. And what we do is, for each layer, we can force it after training to only carry information, and then we can measure the resulting loss, and we see how much has it changed. And we find that on the simpler MNIST task, the network learns to use only the first 15 layers, and changing the rest of the layers doesn't affect it much. But on the more complex CIFAR100 tasks, it learns to use more resources and uses almost all the layers. So highway networks represent a more flexible class of neural network models. It is already being used by people for things like speech recognition and language modeling. And if you want to find out more, please come to our poster tonight. It's poster number 4. Thank you.
Hi, I'm Dan Rosenbaum, and this is joint work with Yair Weiss. So if we have a generative mixture model and we use it for inference, every data point is assigned to the mixture component that best describes it. This means that in inference time, we need to go over all the mixture components, as illustrated here on the left. In contrast, if we use the mixture of experts model, which is shown on the right, data points are assigned to experts according to a gating network that was trained in advance. In our work, we take this 25-year-old idea and apply it to natural image priors. We show that if we have a mixture model prior, we can train a gating network to perform fast inference without harming the quality of the results. So this illustrates how we use our method. Given a noisy image or any corrupted image, one of the best ways to restore the original clean image is to have a mixture model prior over patches of the image and use it for map inference. So this is shown here on the left. And like I said before, one of the steps of inference is to assign every patch in the image to the mixture component that best describes it. So this red-green figure shows the assignment for every patch using a certain color coding. On the right, we also show the assignment of patches, but now it was performed with a gating network that was trained in advance. And this is done with much less computation, and we can see that the results are very similar. The bottom figures also show that the results are very similar it's the restored images in both cases, and they're also very similar. So the full inference here on the left can take a lot of time to compute. So typically to restore this image, it will take about 30 minutes. And using our method, we can do it in less than 10 seconds. So this can be pretty significant. So using our method with a Gaussian mixture model prior, we achieve both fast inference and state-of-the-art performance. And this is true even when we compare to deep architectures that were specifically trained for a certain task. Our model still has all the advantages of generative models. This means that we can use the same model to do different restoration tasks, like image denoising with different noise levels, image deblurring with different blur kernels, and more. So the middle figures here show different deep architectures where each was trained for a specific task. Our model is that the results are here on the right, And it's the same model that was trained only once for clean images and used for different tasks. And we can see the results are comparable and sometimes even better. So we have also code available online, so feel free to use it. Thank you.
Hi everyone, I'm Adrià Recasens and I'm here presenting our paper entitled Where Are They Looking? This is joint work with Aditya Koshla, Carl Bondrick and Antonio Torralba. If you look at these two images here, it is actually really easy to infer where this people is looking. In the image of the left, you have these two persons watching the TV. In the image of the right, you have these two kids looking at their food. This task is commonly referred as gaze following, and it has interesting applications in understanding people's attention, intention, and activities. The goal of this paper is actually build a computer system able to follow gaze. And to tackle this problem, we first decided to build a large-scale dataset called the gaze follow dataset with 130,000 people on it in 122,000 images. The dataset is available for download in our website. Unlike everyone else in the room, we decided to use deep learning to solve this problem. We actually got inspired on how humans might perform this task to build our architecture. So if I now ask you where the person next to you is looking, you would first look at their head, and then you will try to infer their gaze direction. And finally, in that direction, you will try to find a salient object that they could be looking. Inspired by this idea, we divided our network into different pathways, the gaze pathway and the saliency pathway. The gaze pathway uses only a crop of the head of the person and the head position, which is the information that we actually use to infer where the gaze direction is going. Furthermore, the saliency pathway uses the full image, which is the information that we as humans use to find salient spots in images. Finally, these two different representations got multiplied and the final output is computed. What is really interesting here is that if we train this network end-to-end, these two different representations emerge automatically. So if you see in the first row of examples, we want to predict the gaze of the girl in the right. The gaze representation, which is called the gaze max here, indicates us the gaze direction of the girl. The saliency representation highlights the salient spot, which are the head of the two girls and the hands of the two girls. And finally, if we multiply these two different representations, we get the product where we have enough information to predict where this girl is looking. So finally, here we show some results of our system. In yellow, you have the real output of our system. In red, you have the ground truth annotated by humans. If you want to see more of these results or you want to check out our really, really cool demo of this system working, please come visit us in poster number 2. Thank you very much.
So hello everybody, my name is Pedro and this is a work that I did together with Ronan Colobert and Piotr Dolar during an internship at Facebook. So out of the most common visual recognition tasks, we are interested in object detection with segments. So basically, given an input image, we'd like to generate the masks which fully contain all object instances in that given image. We believe that our work is an important step toward dealing with this problem. So here we propose an object proposal algorithm, which is able to find strong regions in an image which are very likely to contain objects independent of their categories. In the past few years, there's been a lot of work on this area, but they usually rely on very low-level vision cues, such as edges and superpixels, and which has a very small learning component. So in this case, we try to a model with convolutional neural networks, which of course have a very strong learning component, and we noticed that it performs quite well. That being said, the question is, how can we set this up as a learning problem? So as I said before, the model is a convolutional neural network, but in this case, it's divided in two different branches. So the top branch is responsible for generating a segmentation mask of the input patch, while the bottom branch it's responsible to give an objectness score of how likely that input patch contains an object fully contained on the image and is located in the center of it. So in the scheme, we have our training data contains three different values. The first one is the input RGB. Another one is objectness score information, which holds the information of there is an object fully contained on the image and located in the center. And finally, in case there is an object, a segmentation mask of that object.
The train is done jointly by minimizing a sum of logistic losses, one for each pixel location in the image, and also one for the objectiveness score. And this is trained by stochastic gradient descent as usual. At test time, we apply the model densely so that you have a segmentation mask and an objectiveness score at its location of the test image. And we also apply it in different scales so that we can detect objects of different sizes. And then finally, to get the top K proposals, we simply get the masks corresponding to the top K scores generated by the network. To conclude, we propose an algorithm that is able to learn to generate object segments. It achieves a very high recall with a very low number of proposals, and it surpassed the state of the art by a big margin at different data sets. So if you're interested, please join me at poster number 8 tonight so that we can talk a little bit more. Thank you.
So, hello everyone. I am Jan, and I would like to present work done with my excellent collaborators, Dima, Kyungyun, and Joshua, on how do you apply soft attention models to speech. So why would you do it? Well, mainly to see how it breaks, because you have those two problems. You have repeated contents, repeated sounds, and then you typically want to scale to much longer inputs at test time than you had during training. So first, about choosing content. The classical model at each step would go around the source sequence, look at the content, see which frames it likes, and then select those. So obviously, if you have the same content, it may not distinguish between them. So we add a little location-aware mechanism that can also tell frames based on the location relative to the previous selection. And this helps with the repetitive content problem. So then maybe the more important question, can you apply this to something much longer than your training data? So it turns out that both models fail, but they fail in a different way. So the content-aware model, the content-based one, learns an implicit location tracker, and this location tracker is very non-reliable. So when you ask it to decode a long sequence, it would first define, and then essentially loop around and loop around and loop around, and there is no way to fix it. Now the location-aware one would do just fine for a while and then refuse to do anything. We investigated the problem. It turns out that there is a softmax over frames, and then the softmax behaves really badly when you apply it to something much larger than your original training inputs. So we have a few fixes for this softmax, and this resolves the problem. In the end, we were able to decode stuff which is 20 times longer than the training data. We got close to the state of the art on Timid, like our fruit fly for speech recognition. We then applied it to Wall Street Journal. So if you are interested in the details of how to do this location-aware thing, which is very generic, it's not only for 1D, it's also valid for 2D things or 3D things, or how to do this for speech, please come to talk with us at poster number 5. Thank you.
Okay, thank you very much. Now the morning session was over. So please join me to thank all the speakers in the morning sessions.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.